This time we are dealing with power functions and regression. So we know what our power function equation is like, and so y equals c times x to a known k power. With regression, that means we're going to put data in our calculator and get our calculator to come up with this equation to model the data. So our data, we have some different cities. We have their populations in thousands. So like Tallahassee is about 48,000, etc. And then we have driving times, and those driving times are an average minutes spent driving to work. So we're going to go to our calculator to find a power function model for this data. So in my calculator, the first place I go is Stat, and I'm going to go over to Edit, and I'm going to type this data into List 1 and List 2, and you can see that I actually did that before starting the recording. So then I want to go back to Stat, and I want to go over to Calculate, and this is the different regressions that my calculator can do, and I want to look for a power regression. So it is option A, power regression. And so I'll hit Enter. One of the options we have is to store this regression equation so that we can work with it in the y equals. So I am going to do that, and I do that by using the vars button, going over to my y variables. It is a function, and I'll store it in y1. And so then I want to do the calculation, and we see the power function. So our constant here is 3.40, and our exponent is 0.184. So going back here, calculator, find a power function model. So we found y equals 3.40 x to the 0.184 power. All right. Next question, how does the actual driving time for Pittsburgh compare to what your model predicts for Pittsburgh? So Pittsburgh has an input, a population value of 1804. So we'll go back to our calculator and see if we can figure out what's going on there. So here in my calculator, I'm typing 3.4. And that's going to be times the population of Pittsburgh, which was 1804. And that is to the 0.184 power. And we'll hit Enter. And so we get a driving time of 13.51. So we calculated or predicted 13.51 minutes. And we find that it is slightly longer than the actual. And so you might be thinking, well, why would that be? And it would be because our data over here is approximately a power function instead of exactly a power function. And we've looked at that with other things where we're using a line or we're using an exponential model to approximate data, but it's not exactly hitting every single point. And so then our last question here is, if you move to a city whose population is 25% smaller than your current city's population, by what percent will your driving time decrease? So it looks like an innocent question. Really, there's a ton of stuff going on. So first off, we want to use that homogeneity principle. And I don't think I spelled that right. But that is, if you multiply by a factor, then you have to do that factor to the k power. So because we have to multiply by a factor, we have to figure out what we would multiply to make things 25% smaller. So smaller is the same as a decrease. That means that a, our factor, would be 1 minus a percent. So I'll take 1 minus 0.25 for 25%, and that means that I would be multiplying by 0.75. If I multiply something by 0.75, my impact would be that I would make it 25% smaller. What I'm multiplying is this x inside the parentheses, so the impact of that would be 0.75 to the 0.184 power, because the multiplication is happening inside the parentheses where the exponent applies, and that is what we have in the homogeneity property. So when I do that math on my calculator, I get 0.948. So 0.948. So this means my time is 94.8% as long. So all I did here is change the decimal to make this a percent, and this is the impact, so it's this many times as long. But that's not what the question actually asks. It asks me by what percent will it decrease. So this is the percent that still remains. To figure out the percent of decrease, I have to take 100%, my original driving time, minus this, and that gives me 5.2% is the decrease. So a lot going on there, going back and forth. So let's review. We know that the homogeneity property tells us that if you multiply by a factor, then the output is going to be that factor to the k power as much. So we have a percent, and we figure out the factor for it. We know if a is our factor, and we use that in exponential models. So we take 1 minus percent as decimal, and that means we're going to multiply by 0.75. In our formula, that would be taking 3.4 and then 0.75x to the 0.184 power. This 0.75 is inside the parentheses, so that exponent applies to it. So when I do that part, the 0.75 to the exponent, I get this value. That value is the number of times as long. And so I changed from decimal to percent. The problem asked me for the decrease, so I took the 100, subtracted this out to get a 5.2% decrease.